See, this is an image. Can you see that image?
Mm-hmm.
Can you see this image of tiger?
Yes, yes, yes.
Yeah.
Tell me.
So now see what is the size of this image. If I will show the
Dimensions.
dimensions, yeah, yeah. So you see this tiger image is of 100 1280 into 720p, right?
Yeah.
1280 into 720, right? Now
Mm-hmm.
each pixel is RGB, red, blue, and green. You can see na, the color, the pixel color is of this RGB format, if you know. Each of these are red, blue, and green is 1 byte. This one also 1 byte, this one also 1 byte. So basically each pixel will take 3 byte probably. Okay.
Okay.
So in total how much they will take? 1280 into 720 into 3 byte. 3 byte means like R1, G1 and B1.
Okay.
Okay. Now if you see this, so the what is the size of this image?
One
One
1.7.
1.757 MB, right?
Oh, yeah.
This is in KB,
Mm-hmm.
1757 KB. You can say 1.7 MB. Now
Okay.
let us suppose you are making an application, maybe an Android app or anything, where you cannot allow this much. Uh, I mean, memory. Like in Gmail, you have a limit of 25 MB, if you remember, if you know. Like
Mm-hmm.
if you
Yeah.
have more than 25 MB file, you have to share it through Google Drive or something. In email,
Yes.
it cannot go. So so
Yes.
just like that, suppose your app has a limitation that you can send you can send an image of maybe 1 MB max. Now such a high resolution image you cannot send, right? Why you cannot send?
Yes.
Because because it's
Out of
the
limits.
size is like limited to 1 MB. So what to do? So what we want is that some kind of compression algorithm where the image will remain as it is. At least the image we will whatever image we will see, that will look like same, look similar. In fact exactly similar it will look like. Maybe probably there will be little difference, because anyway if you are doing a huge compression, some information you will be losing, isn't it?
Mm.
There will be some information which you will be losing. Okay. But the point is that if you can make a image that is a compressed image with same number dimensions, you are not going to resize it. You are not going to change the dimension. The dimension will be 1280 into 720 only. But still if you can compress it, that will be huge. And without any major changes. The point is without much loss of information you have to compress the image. Now, can you see this image? Okay. Uh, can you see this image?
Yes.
Now this image and this image. Sorry, which one was that? See this image and this image. They both look similar.
Yeah.
See this one. What is the size of this reconstructed tiger? Same.
Two.
1280 into 720, right? And what is
Yes.
the dimension is same for the tiger, which is this, and for the reconstructed tiger, which is this. But you see the size. Size has almost reduced by 1/4.
Yes.
4x compression you are able to do here in the PNG images. So this type of compression you can do with K-means clustering. Okay. Uh, so I showed you what will be the input to our algorithm and what will be the output. So input will be an image, some high resolution, high dimensional image, which will be of course taking a high space also. But the output will be a reconstructed or say a compressed image which will be of same dimension, but the space taken by it on maybe hard disk will be less. Okay. Now having said that, I will just I will just discuss you a small thing that forms the basis of this algorithm actually. So in any image, how many colors do our eye perceive? So actually I was reading somewhere, I do not remember the number, but any image, any colorful image you see, your eyes cannot visualize more than uh, some 8 or 10 or something like that, this many colors at one time. If you are looking at a very colorful picture which has lots of color, still at one time your eyes cannot recognize more than 8 or 10 colors. That's the fact. Okay. Now you just if you see, you have each pixel has RGB. Now 1 byte, when I say 1 byte of R, what does that mean? 1 byte of R, it means 1 byte means 8 bit. 8 bit means 2 to the power 8 combinations you can make. 2 to the power 8 means in total 255 values you can put, isn't it? With 1 bit,
Yes.
how many you can put? With 1 bit, 1 bit will be like 0 or 1. 2 bit, 2 bit will be like 0 0
Zero.
0 1
Zero. Zero. One.
1 0 1 1. Similarly, with 8 bit you can like this four numbers you can show na, like with 8 bit you can show 255 numbers. Now you see red is 255 various intensity levels you can show in R. Similarly, G is also 1 byte, that means 255 levels. B is also 255 levels. So many intensity level you can show in an image. If you if you do the permutation and combination in this, see RGB, the value of RGB makes the color of one pixel, right? Each pixel is denoted by RGB values, right?
RGB.
Each R, G and B, some combination is defining some color. If you apply permutation and combination, there can be 255 into 255 into 255. These many colors can be possible. You can portray these many, it is possible to show these many colors in an image, because there are 255 various intensities of red, 255 various intensities of green and blue. And if you multiply them, it will be huge. I mean, it will be around how much? It will be around 12 or maybe 14 lakh or something crore. 1 crore 40 lakh colors. Even there are not so many colors. So what I am telling you is that if you apply permutation and combination purpose, and by that if you are looking at, you will have lots and lots of color to portray. But anyway, our eyes cannot see more than 10 or 11 colors. That's the fact. the fact is the fact is our eyes cannot um, uh, see more than 8 to 10 colors at a time. Maximum maybe say 32 colors. Why do you need
Okay.
to maybe maximum say 16, 20, 32, 64 colors you can have in an image, right? That would be
Mm-hmm.
sufficient. Why do we need such a huge number of color combination like 255 into 255 into 255? We don't need that, right? So
Okay.
so the idea of compression is, can can we can we do something in this, that each pixel is not denoted by 3-bit RGB, rather it will be denoted by maybe just 32 or 64 distinct colors. So instead of using so many color combination, can I use just say 64 color combinations? Because that would be anyway sufficient, right? So instead of using
Okay.
so many colors, just if we can use 64 combinations. Now, what is the idea for doing this? The idea is, take every pixel. Like there are how many? Like 1280 into 720. Take all the pixel and cluster them into 64 cluster. Find groupings in 64 cluster. What to do? Find 64 clusters. Okay.
On what basis? What is the criteria to
The criteria
get it
is,
as 60?
all the pixels I am taking, whatever number of these, whatever these pixels are, like 7 lakhs pixels are there or whatever number is, all the pixels I am clustering them, I am grouping them with k-means on the basis of their RGB. So suppose see, when I say RGB, if R, G and B are 000, what it is going to be? Which color? All zeros.
All zeros. Black
Yeah, all zeros black. And all
and
255
the white color.
is the white, right? Now let's say if I just increase this to 001, what will happen?
Two
Or
zero.
say 111, or say 101, what will happen? It will still remain black. Very less, change in the pixel do not change the color much. I mean, at least your eyes cannot perceive that. Your eyes will find it black only. Got it? So
Okay. Okay.
the point is, can we do something like, that's what I was asking you earlier. In any image you take, Any image you take, whatever image you can see in your home or in anywhere, in office or anywhere, how many color do you think that a photographs contain? Even if you start counting, maximum you will find 20 or 30, not more than that. Even if you count the shades, you will find maximum maybe 40 or 50 or something. Maximum, even if you count all the shades. Because you are, and actually if you find, actually if you will see, you will find that there are lots of colors in that, but our eyes cannot perceive the difference between 000 and 101 or 111, because there is not much
Okay.
difference unless and until there is a huge, I mean, good change, good amount of change in the pixel values, it won't find the change. That's so what I am trying to tell you here is, the anyway in any photograph there are, say, let's say maximum 64 colors, maximum 64 shades, colors, everything. Now, can we do k-means clustering over these pixels in 64 clusters, so that the similar color, all the similar color pixel will club together, something like that. And then what I intend to do is, for every pixel I will just keep the information of cluster. No RGB value I will keep. No, nothing. No R, no G, no B. I will, for every pixel I will just keep which cluster it belong to. Just 64 values I am going to keep. And that 64 values I can present, I can show it in just 1 byte. So 1/3 compression means it's here only. Instead of showing it by 3 byte RGB, I am just showing it by 1 byte now. That is just, that too just 64 values, not 255, just 64 values. Now, the second question is, I have to also store a code book kind of thing. That is called a code book. What is that code book? That all these 64 color, whatever the 64 clusters has come up, what are those colors? Like the first cluster is about red, the second cluster is about yellow, the third cluster is about light green color, fourth cluster is like, say, some dark shade of maroon. So like that you have 64 colors, so you have 64 clusters, so you should know which cluster is what color. So that code book we will store. So for each, like this, for each cluster 1, 2, 3, 4, like for all 64, we will keep the RGB values, that it is red, green or blue, or whatever shade it is, RGB values we will store. This will be our code book. And image we are just going to store in 1280 into 720 into 1 byte. Just that.
Hmm.
Okay. So let us go and do it. Now you see, the program which I have started here. Okay. Initially, this, like sklearn, there is something called as skimage. Okay.
Okay.
So uh, so this skimage basically is the similar as, like, from escape group only, like these people only have developed this, so it is for image purpose. So from there I am just reading that tiger image. Okay. And so if I do image, so this will show you the image. Then if I do this shape 0, shape 1, I will get 1280 into 720 here. Okay. Then what I am doing, like 1280 into 720 I had, not 1280 into 720.
720.
So I will, this image, rectangular image, I will flatten it. 0 to whatever this 1280 into 720, whatever 70,000 or 70 lakh, whatever it comes. I will flatten it, right? Because I have to make the vectors, no? So that I can perform k-means. So this I have flattened. I have reshaped the size of image. Now from 1280 into 720, it will become this much. Some 84 lakh or 84 lakh into 3. 3 because RGB. Okay. So
Shape 0 is a 12.
now it will become a matrix like this. So this will be R, G and B values, and here will be all the pixel values. This will be from 0 to 1280 into 720. Whatever value comes out to be. I do not want to calculate it now. Yeah, you were saying something.
Open the Python code. Python. Yeah, you said image dot shape of 0 is a 1280,
What?
and image of shape. You said that image of shape of 0,
Yeah.
bracket 0.
Yeah.
It is 1280,
Yeah.
and image of shape 1 is 720,
Mm-hmm.
and that 2 you reshape by value 3.
No.
Is it right?
No. This
Okay.
image shape is 1272, I mean whatever it is, 1280, and this is 720, right? So I have multiplied both of them.
Okay.
So this will become something like 80 lakh or something, okay? And this
Okay.
comma 3 is because the third dimension, the RGB, that is also there. Na? It's a 3D array.
Okay.
Length into breadth into RGB. So there are 3 values. So that's why the 3 comes. So that is why that is what I am telling you. Earlier the image was like this: 1280 into 720 into 3. Now it becomes, it's this much into 3. It's a 2D matrix.
Okay.
These are my vectors. These are the features: red, green, and blue. Got it?
Okay.
Yeah. So basically, I am flattening the image in a 1D. So the image is a rectangle, na? So that I am flattening. The only thing is because RGB there are 3 values, so it will be still a 2D thing. Okay. Now I am taking so let's say I will take 64 cluster. Okay.
Okay.
And number of repetition I will say put 1. Okay, just one time I will do that. Okay, so this is like initialization. I told you yesterday also, na, like random initialization. So you
Yes.
put k means 10 numbers of time, and then you choose that random initialization which gives you the best result. So anyway, I am doing here only one number of time so that we do not waste much of the time. So see what I am doing. I am initializing the k-means with 64 cluster, and I am fitting that image into this k-means. So image is what? Image is now 80 lakh into 3. So basically it is clustering of all the pixels, and whatever pixels are of similar color, they will club together. I will run this program, okay?
Okay.
It will take some time also, so we will keep on running it. So see, here I am fitting this image 64 with 64 clusters, and I am printing the cluster centers also. So cluster centers means all the 64 centers RGB value will be printed. Whatever RGB values, red, blue, green values will be there, they will get printed. Okay.
Okay.
So so this is one thing. So all this, for all the 64 clusters, you at least know the colors now with this cluster centers. With the cluster centers, you know that which color that cluster belongs to. Okay. So now what I have done, that all the 64 colors I have converted into uint8. I mean just 1 byte. This is 1 byte. uint8 is a data type which takes just 1 byte. So I have just put it in 1 byte, these clusters. Okay. And k-means.labels. K-means.labels gives what? For all the pixels, 80,000 pixels, for all the 80,000 pixels, for all the 80,000 pixels, which cluster they belong to out of 64, like 1, 1, 1, 1, 2, 2, 2, 4, 4, 3, 64, 59, 58, which cluster they belong to, each pixel it will tell. The labels, k-means.labels. Labels, cluster centers, all are the attributes of whatever model you have fitted. So cluster center is what? See, I will tell you. Cluster center is like this. So let's say you had 8 cluster centers. So these are the cluster centers. Like you have this RGB values over each one of them. And labels are like, see, there are 8 clusters, but there will be points now which belong to these clusters.
Yes.
Yeah. So these are the points which belong to these clusters. Now k-means dot labels. What does it this gives? For all these points, it will tell whether this is this cluster or say this cluster or this cluster. For all these small points, it will tell the cluster for all these points. And k-means dot cluster gives what? These 8 RGB values of these 8 clusters. Okay. So basically here what I am doing, I am just converting them into 1 byte. First of all, the labels also. So how many labels will be there now? K-means dot labels. 1280 into 720 pixels were there. So those many data points were there. So 1280 into 720 labels will be also there. So that I will just know which cluster they are out of 64, and I will save it in 1 byte. I will reshape it in rows into columns. So basically I am again making it as an image. And this compressed, this labels, which is actually a compressed image now, which only keeps value between 0 to 63 labels basically. That is a compressed tiger PNG. And the clusters, what color they are, the clusters centers, the cluster centers, what color they are, that is a codebook tiger.mpy. In this codebook I am saving. So two things basically I have to save now. Okay, one is this codebook, another is this kind of figure, compressed tiger. This figure is nothing but just 64. Each and every pixel is just containing 64 values, which cluster they belong to. What cluster they belong to, that is only there. Okay. So that is two things. And you see the size. The interesting part is this is of 1 KB because it's nothing, 1 byte 64 values, and this is like 251 KB. So these two things, see, when you compress it, these two things will be saved. Okay, you got till now, did you get or not? So,
Okay.
when through an app or through an email, you have to send the image. You have got the PNG image which you have to send to me maybe. So what you will send? You will only send these two things: the code book, I mean all the 64 clusters, what color they are, that code book, that is the cluster centers, and the compressed tiger.png, like all, for all the pixels, what are the labels, what are the clusters they belong to. So these two things, which is of just 252 KB, isn't it?
Okay.
See,
64.
251 and 1, 252 KB. See, this is the image, okay? Now
Okay.
I am performing K-means over there. So what do you need to send? You just need to send me these two things. Plus, you will also send me a program to decompress the image so that I can see the reconstructed image. Are you getting my point? See, when you have a say 20 files, what do? If you have to send it to your boss, what do you do generally?
Zip
We
it.
zip it, we take all the 20 file, or we will tar it, or we will tar zip it, right?
Yes.
And that tarred thing, that zipped file, you cannot see. I mean, no one can see until and unless they unzip it, right? Or untar it.
Yes.
So if you are
Yes.
working in a Linux, once you tar and dot zz or whatever you do that, if you do the zzip,
Okay.
then you send that zzipped file. Nobody can see that zip file until you unzip it, right? And
Yes.
you had a say 100 MB file, and when you zipped it, when you unzip it, I mean gzip it, it will become, that 100 MB file will become just 50 MB or say 70 MB compressed image, compressed file. And that 70 MB file,
Yes.
compressed file, you can send it to your boss, and then your boss cannot directly see that. Your boss will again uncompress it, unzip it, and then he can see the same thing, right? That happens.
Oh yeah.
Similarly,
Yes.
I am telling you, you had an image of tiger, you first zip it. Zipping means just run this program. So when you are clicking on compress button, basically nothing but this program will work. Okay. So this program will basically compress it, zip it, and compress it, and it will make this. So basically this is your zipped file now, compressed file. So basically compressed file means this 1.7 MB has become now 328 KB maybe,
Okay.
and 1 MB. So 329. That's it. Okay.
Okay.
So this is the zipped thing. Now this thing you send it to your boss. Now the boss will unzip it, right? Then only he or she can see that. So unzipping means decompress. So he will run this program, and he will get the reconstructed image. You see, when you run this program. See, this program is running. So whatever you have sent, na, codebook.mpy, that is getting loaded. The compressed tiger p.png, in which each pixel contains only the cluster, which cluster they belong to. That information is contained. So that is getting read in this. And then you are basically, what are you doing? You are saying that first pixel is of say second cluster. So you are looking at the RGB value for second color cluster from this code book, and you are putting that RGB there. So like that you are reconstructing for all the pixels. See, this is a
Okay, but what is that?
reconstructed image. So your boss has only this codebook tiger and compressed tiger. But when he ran this decompression algorithm on this, it generated this reconstructed image from this, and then they can see that what you have actually sent. And the same fundamental, same logic actually happens when you do the zipping or tarring or the zzip or whatever you do in Linux or in Windows for compression. We have a lot of compression algorithm, if you know, right? So there are a lot of times we need to compress something and then send because of some limitation, or because maybe you want it to upload fast or something. So if you have hundreds of files, you cannot keep on uploading everything, right? What you do is you will take that whole folder, and whole folder you will zip it and then you will send. So that's what I am trying to tell you, that the same funda has been applied here also. You first compress it. Now the compressed thing you cannot see. Use that compressed thing to decompress it, and once you decompress, you can reconstruct the image which has been earlier compressed. See this one. And how it is done? It is
But
very simple. You have this code book now.
yeah, what is that file content?
See,
Codebook.tiger
this
MPI.
code book is like, in this code book you have this 1, 2, 3, 4, like that you have 64 centers, na? 63, it will go till 63 because it has started from 0. So 64k means clustering we are done. So for all the clusters, the codebook contains the RGB value, which will tell that which color was that cluster, which color was that.
Okay.
Okay, and this compressed tiger contains this compressed tiger.png contains an image like this,
Hmm.
where each pixel, you see, these are the pixels which I am trying to draw. So this each pixel contains just 1 to 64 values. Sorry, 0 to 63 values. Okay. So for each pixel, you know that this is 7 cluster. It belongs to 7th cluster. So from codebook, you will see that 7th cluster is which color, which RGB. RGB denotes the color, no? So
Yes.
that RGB you will put it here. So whatever 64 clusters are there, no, that color RGB will be replaced here. So these 64 colors will be spread out in that image, and that will be your reconstructed image. So the reconstructed image, see, that's what I was telling earlier also. This image, the reconstructed image, whatever you have seen, this image only has 64 different colors. That's it. How many colors this have?
Okay. 64.
64 only. You understood how this is happening?
Yes,
Maybe
yes.
I will tell you the compression once more. I have done nothing. I have just, you see this image shape, image dot shape. I have flattened the image first, 1280 into 720, that I have multiplied. It will maybe come around 80 lakh or something. Okay, and
Hmm.
that into RGB, whatever the three RGB values were also there, no? So it will be a big matrix with total number of pixels into 3 RGB. Total number of pixels are how many? 1270 into 720. 1280 into 720. Okay, that I have clustered in 64 clustered, 64 groups. Now what I am trying to say here is just try to understand. When you cluster the whole number of pixels, so many pixels, 80,000, 80 lakh, whatever it is, so many pixels into 64 clusters, it will have 64 centroids. 64 means what it will do? Initially 64 values it will randomly throw, right? And then it will try to assign and update, assign, update, assign, update. In iterations it will try to find the clusters. Isn't it? That is the cluster centers. That is cluster centers.
Center.
And so that is what I was telling, cluster centers, the mean. And labels are what? All the pixels which cluster they belong to in k-means. That is labels. So I will just suggest you that you just try this program maybe on your own. You will certainly understand more. You will get more insight of it, that what I actually am trying to do. And by default, all these pixels are float type. Float takes 4 byte. So that is why it is necessary to, this cluster centers or labels, it is necessary to convert them into a 1 byte figure, a 1 byte data type. Because when you convert them into 1 byte, then only it will become 328 KB. If you are still using float, it will be high. It won't be compressed. Okay.
Yes.
Basically, each pixel now I am denoting by just 1 byte. Earlier it was 3 byte because you had three different color RGB. But the point is that why do we need three different color RGB and all? Why do we need 255 into 255 into 255 number of colors? We only need 64 colors, because any photograph you take, it can maximum have 64 shades of color. Or maybe 128 you can keep, if you are like, no, 64 won't suffice. So instead of using 255 into 255 into 255 combinations, I am limited to 64 or 128 colors. That's it. Because anyway, any photograph will not have more than that colors. So that's why I am performing k-means clustering with 64k on all the pixels. So all the pixels of similar color, similar RGB, because you see what is the feature here? RGB, right? You see now the number of pixels into 3 is the dimension. So all the pixels with similar RGB will come together in a cluster. That cluster color RGB value, that cluster mean, I am saving it as a code book. And for each pixel in which cluster they belong to, that I am saving in another compressed thing. Now with the help of these two, I can decompress the original image, right? In decompression
Okay,
also, I just loaded this tiger and compressed book. I again made an image of, you see, 720, 1280 into 720 into 3. It's a three-dimensional array of 1 byte each. And what I am doing? I am saying that in this C image, the compressed image, just go through each pixels, then go through each rows and then go through each column. Then for each pixel, whatever the cluster is among 1 to 64, it will give. That clusters the color, I mean the centers, basically centers are like the color, na? So the color of that cluster, you put it in that image, the RGB values. So once you put that RGB values at each pixel, it will form the reconstructed image. Did you
okay.
get my
What
point?
what does this colon stand for?
Which one?
Colon in image ij
Colon,
and colon.
colon is like all the three values RGB.
Okay, okay.
Like if you remember in Python, I told you, like if you, where is the IPython console? I will show you. Suppose you import NumPy, right? Now suppose you made an array np dot random dot like this.
Hmm.
Okay. Now if you put it like this, it will show you everything, right? Now if you
Okay,
put
yeah.
say 1 comma, first
Yes,
row, all
first.
columns.
Hmm.
So both the column.
Yes, yes.
Sorry, it starts from 0. Okay, so first will be this.
Okay, okay.
If I say first row, all column. If I say all rows, but first
Colon,
column,
colon.
right? So it will give
Hmm.
this. If I say all
Okay.
row, but sorry, yeah, this one is the first column. You see this one.
Yes, yes, yes. Got it.
So that is what it is saying here, that at ij pixel location, whatever the at ij pixel location, this one, whatever is the RGB values, put that RGB values into RGB values of this image, and this image is your
Okay,
reconstructed tiger.
okay.
Okay.
So this compression we use only for image or can use for other like videos or
Only for
GIF?
image, because it is color based. This is in technical term, in machine learning term, if you want to Google this problem, na, you just search color quantization. So if you will search color quantization, na, see, you will find this color quantization example. You see, this is like original data, this is clustered data. This is just one example. Color quantization. See, this image is of you. This image has 19,000 colors. I mean the shades. You know, I told you na RGB encoding is 3 pixel 3 byte RGB. So it is like having different shades. I mean the intensity values are varying. So can you find any difference between this and this? This and this? No. Because
No, no.
anyway in photograph you cannot see, I mean there will be only say 64 or say 30 20 30 colors. See, this is a quantized image with just 64 colors of k-means and it looks exactly the same. Okay,
Yes. Yes.
so this kind of compression is color based quantization, color quantization thing which you can do in images.